Here we go, because we're trying to build to some cool applications. So last class, we defined the GCD, prime numbers, and relatively prime. So I'm not going to define them again. These are actually things that you've used, concepts from like your elementary school, not maybe elementary school, but these are ideas that are introduced in like middle school math. Now we're going to use them for some higher level stuff that you couldn't teach a sixth grader maybe. But these are ideas. Like I think you guys are familiar with prime numbers and the prime decomposition. So we also stated what's called the fundamental theorem of arithmetic. And so you should be familiar with that. Essentially what it says is that every integer, particularly positive integers, can be expressed in a unique way as the product of primes. Does anybody have a question about any of this stuff? Okay, so what we didn't talk about yet is, and so we'll define it now, is a closely related concept that you should also be familiar with. And that's the least common multiple. So the least common multiple of integers, I'll use A and B, is the smallest positive integer. That is divisible by both A and B. So again, a concept that was introduced to you, I would imagine in middle school sometime. You work with these ideas. And don't forget, we're not trying to relive middle school math here. What we're trying to do is we're trying to make the fundamental definitions for these important concepts in what we call number theory. And we're going to build to be able to do things like solve congruences. So I alluded to this last week, where in normal algebra, we can solve an equation using these basic facts, where if I have an equation, I can add the same thing to both sides and it doesn't change the truth of the equation. Or I can subtract the same thing, or I can multiply or divide. Well, that doesn't necessarily work with congruences, as we showed you on the homework. You don't get to just do a cancellation law like you do in the normal number system. And so we have to understand when we're legally allowed to do that. And part of that process is understanding these notions of primes, numbers, these notions of relatively prime. And of course, what comes with that are some basic facts, GCDs and LCMs. So what do? We denote this as, so let's just do a couple examples of very small numbers. So let's take the greatest common divisor of, say, 35 and how about 30? What is the largest number that is divisible by both numbers? Or divides into both numbers, I should say. Well, one way to do this, and let's just kind of beat the dead horse, is let's write this. So a good strategy, and I'm not saying you want to do this necessarily as a human, but think about how you could program a computer to do this if you wanted to. And that is, I can write these guys as their prime factorization. So what's what is 35? Well, 35 is divisible by 5 and 7. That's one way to think about it. 5 times 7. And then what is 30? 30 is 5 times 6. So what is the largest number of those guys? And maybe I should even be a little more clear what I'm doing here. Maybe I'll write this. Whoa. Maybe I'll write it in its complete decomposition. So 5 times 6, this is 2 times 3 times 5. Do you guys see what I'm doing here? And so here the GCD is going to be 5 because it's the largest integer that is the divisor of both of them. Does anybody have a question about this? Okay, so now let's, interestingly enough, what if we wanted the least common multiple of 35 and 30? Well, if we write this out, once again, this is 5 times 7, and then 2 times 3 times 5. And so the answer here is what? Now remember, we're dealing with multiples now, not divisors. So one way you might do this is you might just start writing out the multiples of 35, and then you might write out the multiples of 30 and see when you finally get a match. Now the question is that the most efficient way of doing it? Does anybody have an idea on how to do this? I mean, you could say, okay, 35, and then the next one is 70, you know, keep going, right? Does that seem like the best way to do it, though? Or is there some sort of hidden shortcut? Okay, so think of if a number is a multiple of both 35 and 30, then it also has to be a multiple of all of each one of those numbers divisors. So it has to be a multiple of 5, 7, 2, 3, and 5, right? It has to be a multiple. Does that make sense? Maybe. So if you already have your numbers in the prime factorization, there's actually a really cute way you can, as a human, or program a computer to determine the LCM just by looking at these prime factorizations. So it turns out that this is equal to, let's write down all the primes of all of them. So what's the smallest prime? 2, right? Then it's 3. Then it's 5, and then it's 7. Now, of course, I'm not saying that that is the prime factorization because we have duplicates. Excuse me, I'm not saying this is the least common multiple because we have duplicates. 5 shows up on both sides. So now what you need to do is you look at the exponents. So one way you can do this is you can use a very basic function, and I don't know that you're familiar with it or not. I think you should be. But we use what's called the max function, and it's very self-explanatory. Maybe let me write this a little clearer. So what are the powers? In the first number, is there a power of 2? No, right? Is there a power of 2 in this number? No. So what we're going to do is we're going to note the two powers are 0 and 1. then what is 3? Is there a power of 3 in the first number? No, so it's 0, and there's 1 power in the second number. And then 5, we have a power in each. And then for 7, there's 1 power in the first number and there's no power in the second number. And so this becomes 2 to the 1 times 3 to the 1 times 5 to the 1 times 7 to the power 1. Or if you want, 30 times 7, which is 210. So I don't know if you recognize the pattern I'm using there. If not, you don't have to use the pattern. You can reason another way. But I would encourage you to look at this pattern and think about how I'm getting it. Think about why it works. Don't try to memorize the pattern. Think about what the pattern is. Think about why it works. Stop trying to memorize things. There's one image that I hope you leave with from this class is stop trying to memorize things. You're never going to be as good as it, especially considering you can look everything up now. Okay, any questions about this? All right, so here's a cool fact about the GCD and the LCM. It's a pretty cool theorem. And we'll probably ask you to try to prove it for homework. Theorem. If A and B are positive integers, then their product, A times B, is equal to the GCD of A and B times the least common multiple of A and B. So you should verify that this is true. Pick 2 numbers, pick 2 integers, and verify. Think about how you might prove it. Remember, just showing that it's true for a couple examples is not a proof. How can you prove it in general? Okay. So an important problem in even ancient, can't spell. Should I use the word ancient? Maybe that's a bad word anyhow to use. So in an important problem in both classical and modern, classical is more fancy than ancient. In math and science is determining the GCD. So again, I've alluded to this, and let me say it again. Determining GCDs is not just busy work for a 6th grader. In many applications of number theory, in particular this idea of cryptography or the science of code, it is very important that we know if 2 things are relatively prime. It's very important if we know more than two things are pairwise relatively prime. And so what does relatively prime mean? It means the GCD of two numbers is 1. In particular, in applications in the real world, we often need the GCD of massive numbers. And you're not going to be able to, say, write a prime factorization down of two numbers that have hundreds, if not thousands of digits. So we need a systematic way of determining the GCD. And luckily, there's an algorithm that goes back to as far back as we have written history. And it's called the Euclidean algorithm. So this is the same Euclid from maybe if you've studied any geometry. So it is based off the following important fact, which we will not prove because we don't have the time, but it's not difficult to do. So what we usually do, if there's a result that is sort of used for something bigger, we usually call it a lemma. And so we're going to call this a lemma, not a theorem, because it's really sort of the reason why the Euclidean algorithm works. And so if A equals BQ plus R, and I'm definitely using Q and R as we used them before. Think about dividing B into A. And we know that we can write A as B times Q plus R. So if these guys are integers, then here's a very useful thing to know. The GCD of A and B is the same as the GCD of B and R. Okay, so this, it probably does not seem like this is of any use right now, but we're going to show you how it's of use. So essentially what this lemma tells us is we can determine GCDs by continuing to divide A by, say, B, or whichever number is larger, divide it by the smaller number, and keep repeating the process until we get a remainder of 0. So let's show you how it works on a very simple problem, the one we did before. What was it, 35 and 30, right? So here's how it works. So I'm going to take 35 and I'm going to write it as 30 times 1 plus 5. Then, and this is very similar to what we did the other day, I'm going to take this number and put it here. and I am going to take this number and put it in this position. And so now I'm going to say that 30 is equal to 5 times what? And 30 is equal to 5 times 6, correct? Okay, so what was our last non-zero remainder? Well, we only had one, right? So the quote-unquote last non-zero remainder is the GCD. Now, of course, this seems silly for this particular problem, but when we do it with larger numbers, you're going to see sort of how this pattern gets things done. So look at the previous lemma. Notice right away we had 35 equals 30 times 1 plus 5, right? So in our particular problem, that means that the GCD of 35 and 30 is equal to the GCD of B, which was 30, and R, which was 5. So what's the greatest common divisor of 5? Well, 5 only has one divisor. It's not 1 itself, and that's 5. So the answer is automatically 5. All right, let's look at a much more sort of illustrative example. Before I do that, does anybody have a comment or a question? Going once, going twice? All right, let's do another one. So we'll do 2 more. So let's say we want to know the GCD, and these are, again, we'll choose little smaller numbers. How about 27 and 33? So it's not going to take long for you to recognize that the answer here is 3. But let's see how the algorithm gives it to us. So we take the larger number, and it's equal to the smaller number times, you apply the division algorithm. So this is 1 plus 6. And so then next, it's 27 equals 6 times. Well, how many times does 6 go into 27? 4 plus 3. And then we repeat the game again. This is 6, and that's 3 times 2 plus 0. And so let me also annotate where these numbers are coming from. This number moves here, this number here, this number here, this number here. And so this guy is the last non-zero remainder. And so the GCD of 27 and 33 is 3. Does anybody have a question about this? Okay, so an interesting thing is that we want to know the GCD of something. And then what turns out to be even more useful in many applications is not just that the GCD is a number that's associated to these two numbers in a specific way, but another important sort of way to think about this is that we are going to be able to take any GCD, or maybe a better way of saying this, let me rephrase. We're going to be able to take any two integers and write them in a creative way, which we call a linear combination, in terms of the GCD. So let me illustrate it sort of the following way. So if I go back, let's what we'd like to do is we'd like to reverse the steps in a creative way. So sometimes it is useful to sort of reverse the steps in a creative way. So what do I mean by that? Well, here's what I'm going to do. Let's write down the argument again. So what was the argument? Well, we had, what was it, 33 and 27? Is that what it was? Yeah. So we had 33 was equal to 27 times 1 plus 6. And then we had 27 was equal to 6 times 4 plus 3. And then we had 6 is equal to 3 times 2. So that was the process that we took. So what I'm going to do now is I am going to look at this second to last line. I'm going to start here. And I'm going to rewrite it. So, and I want to rewrite it and I want to solve for 3. But I don't want to just solve for 3 and say that 3 is equal to 3, because if I do that, I mean, that's not giving me any information I don't already know. What I want to do is I want to quote unquote solve for 3 so that I get the numbers 33 and 27 involved. So let's solve for 3 in terms of the original numbers, which are 33 and 27. So from the line that I have an arrow on, I get 3 is equal to 27 plus, now watch how I write this. I'm going to write it a little different. I'm going to write this as 4, but it's not 4. I'm going to use negative 4 and then times 6. Just doing it that way. Now, notice that I have my one original number here, but I don't have 33 anywhere. However, if I notice the top line has a connection between not just 33 and 27, but it also has 6. So what I can do is I can come down here and I can leave this as 27. And instead of writing 6, I'm going to write what the top line tells me 6 is. And that is, this is 33 minus 27. Now, of course, you're going to say, why would you write it that way? And I get it. There's no intuition for you to see why I would want to do that. All the right-hand side of this equation says is if you do the arithmetic, it gives you 3. But that's not the point. We know that. What we want to do is we want to represent 3 in an interesting way that's unique to 27. I shouldn't say unique, but excuse me. Something just flew on my nose. If I die, who's going to take over? Wow. Ooh. Interesting. Let me back up. We want to write 3 in terms of 27 and 33. And so we're going to do it like this. I am going to note that this is 27, and then this is plus -4 times 33, and then it's plus 4 times 27. So I'm just distributing this -4. And now how many apples do I have? Well, I have 1 27 here and 4 over here. So now I have 5 times 27 plus -4 times 33. That's pretty friggin' cool. Now look, you can go to the right-hand side and multiply 5 and 27 and then multiply -4 and 33 and add up, it's going to give you 3. But it turns out this representation of the GCD is often useful. And there's nothing special about this problem. We can do this for any 2 integers, A and B. We can always write the GCD of A and B as what we call a linear combination. Does anybody have a question about this? Notice I'm not trying to be coy. Notice I wrote in a creative way. Many students, myself included, when I learned this, and if you try to learn it, you're going to struggle with how you reason what's in red. Any questions, comments? So the above sort of reasoning I did is called the extended Euclidean algorithm. Good news, it always works. And so it's actually a theorem. And it's called Bézout's theorem. Biz, to the French guy. So if A and B are positive integers, then there exist integers S and T such that the GCD of A and B is S times A plus T times B. And so we give a name to these numbers. We call S and T Bézout's coefficients. Anybody have a comment or a question? Okay, so does anybody have anything they want to say? All right. Very good. Okay, so it might seem like we're sort of just kind of just stating things to state them. But we're really not. We're, as I said, we're building to something. There's a big picture out there that we'd like to be able to work with, and that is, as I said, our one of our big goals is to understand common and appropriate applications of this stuff. And the big one is this notion of cryptography. And one of the things it relies on is the ability of us to solve congruences. And we alluded on the last homework that our traditional way of solving equations doesn't work with congruences. And so we need to know when it does work, and if it does, how do we do it properly? And so that relies on these concepts. The big concept is this idea of relatively prime. That is, if the GCD of two numbers is 1. So we need to know when the GCD is 1. And in order to do that, we need to be able to compute the GCD, right? So this is why we're talking about this stuff. We're not just talking about it to bore you. So here's our big theorem about congruences. So suppose m is a positive integer and a, b, c are integers. If AC is congruent to BC mod M, and here's the key fact, the GCD of C comma M is 1, then we can quote unquote cancel the C. So this is sort of like a cancellation law, but it requires this extra sort of piece of information. So I know I keep beating the dead horse, but here's what I mean by cancellation law. When you were a kid, or not a kid, even now when you're solving equations, if you had something like 5x equals 45, you can reason that x has to be 9. But you can't just reason that simply with congruences. Do you understand what I'm saying? Now, the reason this theorem is true is it relies on a basic fact of divisibility. Does anybody have a question about this, by the way? Comments? So we need this extra condition. If we want to sort of quote unquote cancel things like you're used to doing, we need an extra condition. And so we foreshadowed this on the homework. I mean, we did the problem last week. I asked you to do that. Okay, so the proof. You have a question, Mr. Fink, or are you just stretching? So the proof relies on a fundamental lemma. Which is not hard to prove in and of itself. So suppose A, B, and C are positive integers. If the GCD of A comma B is equal to 1, so if they're relatively prime and A divides BC, then we can conclude that A must divide C because it can't divide B. All right, so basically what we're saying is, think about this. Take two numbers that you know are relatively prime, say like 5 and 7. Simple examples. Now note, for example, that 5 divides 40. Okay, what's a factorization of 40? Say 5 times 8. What we're saying is, and this is the thing that you recognize, 5 being a divisor of 40 and being that it is relatively prime to itself, or maybe, excuse me, let me rephrase it. I said that confusing. So maybe I'll just write it down instead of having you try to think about it in your head. So let's just look at an example. So let's say A is 5, B is 40, and C is any positive integer. I'm sorry, what did I say originally? I said 5 and 7. What I wrote down is wrong here. I said let's take two relatively prime numbers. And let's say, I don't want to use any positive integer. Let's pick a specific one. How about 56? No, that's a bad example. Let's do, how about 55? So note that 5 definitely divides 7 times 55, and 5 divides 55. It can't divide 7. So this is an example of, it's not an example of applying the theorem. It's an example of a true version of the theorem. But applying the theorem, think about what we're deducing. What we're saying is if we know a number divides the product of two numbers, think of it from this standpoint. If I know that A divides the product of B and C, but I also have the information that A and B are relatively prime, then the conclusion I make, not even knowing what C is that A must divide C. All right, so we're not going to say anything more about this. Again, this lemma, you should try to prove it. It's the proof of it is, maybe we'll ask you to do it for homework. It's just a pretty simple application of Bézout's theorem. Does anybody have a question about this? All right, so we can now solve congruences, at least simple ones. Ooh. I guess I should say at least simple ones here. So let X be an unknown let A be in C. Well, I guess we don't need a C because we have X. How about, oh, we need a mod, so we'll use them. So let A be M greater than 1 or equal to 1, I guess. Be integers. And then what we're going to do is we call AX congruent to B mod M a linear congruence. So what we need to do if we want to solve this, we need to generalize our notion of how we solve regular equations. Regular equations, we would just divide both sides by A, right? That was the strategy. Or a better way to think about it would be you multiply both sides by the inverse of A, particularly the multiplicative inverse. But we're working with integers here, right? And there's nothing that says if you divide one integer by another, there's no guarantee that what you remain with is an integer. So we have to be very careful with how we do this. So we need some terminology. Suppose there is an integer, I'll denote it with a bar above it. There is an integer A with a bar above it, or A bar, such that A bar times A is congruent to 1 mod m. We call a bar the inverse of a modulo m. So this is analogous to 1/5 times 5 is 1, or 1/8 times 8 is 1. Here's a very, very, very cool fact. And again, this comes from Bézout's theorem, this GCD stuff. It goes like this. If the GCD of A and M is equal to 1, that is, if they're relatively prime, then A bar exists and is unique. Now, when I use the word unique here, I'm using it slightly different than you're thinking of. It's unique up to modulo m. So what does that mean? Well, that means there's actually, if you want, there's infinitely many of them, because every multiple of 1 would be reduced back modulo m to what you started with. So that's going to sound very confusing, but let's look at the example we had from last class. If we took z sub 4, what was just the numbers 0, 1, 2, and 3. Well, we know when we looked at our addition tables that 1 plus 3 is 4, but 4 is not in our set because 4 is congruent to 0 mod 4. So we're going to do an example real quickly, and then hopefully this will illustrate what I mean by that. So let's say this the following way. So unique in the sense that all other inverses of A are congruent to A bar modulo M. So let's look at an example real quickly. So example. We can verify that 3 times 7 is congruent to 1 mod 4. Thus, 3 is the inverse of 7 modulo 4. Now, I just guessed that by inspection. I thought to myself, I picked a number in my head. What number am I going to use for my example? I said, okay, 7. So I said, okay, what multiple of 7 is divisible by 4 if I subtract 1 from it? So the first multiple of 7 is 14, but if I subtract 1, that's 13. The next multiple is 21. And so 21 minus 1 is 20, and that's divisible by 4. So that's how I did it in my head. I'm not saying that's the only way you can do it. And in fact, I'm not even suggesting that you need to know how to find inverses yet. I am just showing you that this is one. That's why I said verify. Convince yourself that 21 minus 1 is divisible by 4, because it is. And so because that's the case, we say 3 is the inverse of 7 modulo 4. Now, another way to think about this, can you think of another inverse? Well, is there any other multiples of 7 that if I subtract 1, they're divisible by 4? Well, what's 30? The next multiple of 7 is 28. 28 minus 1 is not divisible by 4. What about 35? 35 minus 1, is that divisible by 4? No. Is 42 minus 1 divisible by 4? No. 49 minus 1 is 48. That is divisible by 4. So note also that 7 times 7 is congruent to 1 mod 4. So you might say, well, then 7 is the inverse. Right, but 7 in terms of mod 4 is congruent to what? 3 mod 4. So that's what we mean by uniqueness. Yes, I've found 2 inverses, 3 and 7. But 7 in terms of mod 4 is the same exact thing as 3. So again, this is big jumps here for our brains. Look, here goes O'Grady again talking nonsense. You ain't learning this overnight. You're not making sense of this overnight. This stuff is hard to learn. It takes effort. It takes lots of fighting with your brain. It takes lots of feel like you're getting beat down. Feel like you're stupid. You should never feel like you're stupid. You're not. So here's something that's useful. In fact, 7, 11, 15, 19, 23, and this list goes on and on, are all inverses and congruent to 3 mod 4. And you could verify that for yourself. You know, for example, 15 times 7 is 105. What's 105 minus 1? It's 104. Is 104 divisible by 4? Yes or no? Is it? Yeah, of course it is. what, 25 times 4 is, so 26. So again, one of the things that's hard to learn is this idea that we can have multiple inverses, but really we think of 7, 11, 15. They are the same number to us because they're all congruent to 3 mod 4. So when we're using mod 4, what we're essentially saying is we're only using 4 numbers, 0, 1, 2, and 3. That's it. Every other number must be congruent to one of those numbers mod 4. So a fancy word for this is we say congruent classes. So anyhow, this is, I wish it was easy. It's not easy. I remember trying to learn this, so I empathize. So the question is, without guessing and checking, what's a systematic way of doing this? What is a systematic way to determine inverses? You use the Euclidean algorithm. So one way is to use the Euclidean algorithm and Bezout's theorem. That is all that hard work we did. Anybody have a question? So it turns out when you want to solve a congruence, the hard part isn't solving the congruence. It's going to be to find these inverses. Sometimes they're quick and easy. Sometimes there's not. So let's look at an example of solving a congruence before we run out of time. So we'll use the information we had. Let's solve. We had an inverse for 7. So let's say we want to solve 7x is congruent to how about 15? Mod 4. So since 3 times 7 is congruent to 1 mod 4, we reason as follows. We think. So we would take 3 times 7x, and then we would take 3 times 15 on the right, and then we'll reduce down modulo 4. So we know that 21 is congruent to 1. What is 45 congruent to mod 4? Well, what is the remainder of 45 when we divide it by 4? It's 1, right? So we get this. Now, what does this mean, and is it correct? Do we have any loops in our arguments? Does it check out? So another way of thinking about this is if we reason as we normally did, any solution would be congruent to 1 mod 4, if we have one. Or do we have a flaw in our reasoning? Anybody have any thoughts? Well, does it check out? If I replace x with 1, does it work? If I replace x with 1 in the equation, is it a solution? Well, 7 times 1 is 7. What's 7 minus 15? Negative 8. Is negative 8 divisible by 4? Yes, it checks. Is it the only solution? No, it's not. 5 would work. 35 minus 15 is. So this checks. And more is true. And then we're going to end and let you be in fear of how scary and confusing this is, right? So in fact, x equals 4k plus 1 for any n works, or excuse me, for any k works. As long as k is an integer. Now why? Why does that work? Well, because those are all the numbers that are congruent to 1 mod 4. If you subtract 1, you're left with 4k. That's clearly divisible by 4. So any number of the form, think about divisibility, and this is one thing that will help make it easier to learn this stuff. Think about how all this comes back to one of the first things we talked about, which was this silly division algorithm. That any number, it seems silly, but it's not. Any number can be written as a number times a number plus a remainder. So any number on the planet that's divisible by 4, when you subtract 1, it has to look like this. So anyhow, we're past time. I know this is overwhelming. We'll give you some assignment later today. Please try to work on it before Wednesday so you can ask questions. We're getting towards the home stretch. I know you guys are busy, and I know it's stressful. I know Jared just had a kid and all that. You guys, you got a few more weeks of the scariness, and hopefully we'll be better. Anyhow, guys, thank you very much. Please know that this is not the easiest to learn, so don't get discouraged. And I'll see you guys Wednesday. Thank you.